Hi and welcome to the Base 2 lessons series. This lesson's topic is addition and subtraction in Base 2. Objectives of this lesson. We discuss the decimal representation system and some of its features. Next, we study how to represent numbers using only two symbols, 0 and 1. This is called the binary representation. Finally, we study how to add and subtract numbers using the binary representation. Why is this important? Maybe you ask yourself, how come that we learn about math in a programming course? Why is this important? You might be wondering, why would you want to know about numbering system when all you want to do is to write computer programs? This is an important question. Computer parts are engineered to understand only two symbols, 0 and 1. 0 means low voltage and 1 means high voltage. Basically, everything inside the computer software is eventually constructed from only two symbols, 0 and 1. Or, in some other formulation, binary numbers. If you want to instruct the computer, or to be more specific, the processor, to do things for you, you must be able to speak his language. And therefore, understanding binary numbers is crucial for your understanding of anything low level in the computer, especially assembly programs. What I mean by that is that you cannot write assembly programs without having some kind of a basic understanding of what is the binary base and how to work with binary numbers. Numbers which are made of only ones and zeros. Let's begin with something familiar, the decimal representation. We make a daily use of the decimal representation, also known as base 10. It is the most common numbers representation system among human beings. Basically, if you have survived so far in our culture, you probably know how to use it. You can see those numbers everywhere. Decimal basically means 10. The decimal representation uses 10 different symbols, which are the digit 0 to the digit 9, to represent numbers. The significance of every digit inside a number in base 10 is related to its location in the number. This idea is also called positional notation. As an example, if we have this number, 12,513, this number actually equals 3 times 10 to the power of 0, plus 1 times 10 to the power of 1, plus 5 times 10 to the power of 2, plus 2 times 10 to the power of 3, plus 1 times 10 to the power of 4. I want to emphasize that the coefficients that we have here, 3, 1, 5, 2, and 1, are just this number reversed. And if we expand the powers to the results, we get this. And this is the real value of this number. This is just a representation, and this is the value. This is the meaning of this number. Some small comment about it. We can see that leading zeros don't change the value of the number. You probably already know this, but I just wanted to mention this. Why you should care about representation systems? It is easy to underestimate the wisdom in the decimal system. You might not know this, but there were times and places in the history of human beings where people were struggling with much stranger numeric systems. you might have seen the Roman numeric system. Imagine what would happen if you had to pay your bills with the Roman numeric system. Numeric representations are ways to keep in memory or communicate the quantity of something. Which means that if I want to communicate to somebody else some quantity, maybe a very large quantity, I can just take a paper and a pen and then write some small digits on the paper, and those small digits together represent a very large quantity. It is pretty amazing. Another important thing to note is that the quantity and the representation are not the same thing. Some people mix those two things because they only know of one representation for numbers. They only know the decimal system. So they have problem with separating the idea of the actual quantity and the representation. What it actually means is that the quantity is something in the real world. There are some objects that we want to count somehow. Then we have a way to represent the amount of the object, and this is the representation. If there are many grains of sand somewhere, and we manage to count them, then we could somehow represent the amount of grains of sand on a piece of paper. We could just write the amount in the decimal system, if we could actually count. If we could count all those grains of sand. However, this representation is not the same as the actual objects. You got to understand this distinction between the representation and the actual real objects that we count. Another reason for which you should care. If you don't know about any smart numeric system, in order to communicate a quantity to somebody else, you actually have to show him the quantity. And this is very wasteful. Imagine that you want to tell someone about some very large amount of objects. Maybe a pack of stones. Really lots of stones. If you wanted to tell somebody else that you have lots of stones, and you didn't know about any smart numeric system, you would just have to carry the stones to his place and show him the pack of stones, the set of stones. But if you and him both know about some smart numeric system, you could just write the amount on a piece of paper and show him the amount, and then he understands. For example, this is how 23 looks like if you don't know about any numeric system. We can just see 23 objects. Imagine that you could only represent numbers in this way, by painting lots of points on a paper. This would be very unfortunate. What would happen if you wanted to represent 1 million in the same method? It will be pretty hard to do. Last point about why you should care. Different numeric systems invoke different thoughts and ideas about the nature of numbers. For example, I don't get much information from this picture. From this kind of picture, I can only get the feeling of a little or a lot. If I see only a few dots, I know that the quantity is a little quantity. But if I see lots of dots, then I know that the quantity is very large. But, for example, with the decimal system, I get much more information. For example, if I look at this number, 1 million, I know that it is divisible by 10. Just by looking at this number. You probably couldn't get this kind of conclusion if you looked at 1 million in this formulation, as a set of dots on a paper. And I think that this is a very important point. I give much importance to the thoughts and ideas that you get from the representation. Some features of the decimal system. Features that you probably know by now, but I just want to remind you of those features. The first one is that the decimal system allows to represent very large numbers with not so many digits. This is a very important feature. As an example, k digits are enough to generate a number as big as 10 to the power of k. And this is a lot. As an example, k equals 40 would give us really large numbers. Probably more than we are ever going to need. Arithmetic in the decimal system is pretty easy. We already learned at school how to add and subtract numbers in the decimal representation. It is also pretty easy to multiply and divide numbers in this representation, though not as easy as addition and subtraction. As I mentioned before, it is also pretty easy to check divisibility in the decimal system, especially by some special numbers, for example 2, 4, 5, and 10. And maybe a bit more difficult, but also possible to check divisibility by 3, 9, and 11. Let's try to generalize the essence of base 10 to get the good features of base 10 in a more general fashion. Choosing 10 as the base number was pretty arbitrary. Okay, maybe not that arbitrary, you do have 10 fingers. But it doesn't mean that 10 is the best choice. We could choose any other base number to create a new number representation system. As an example, in base 5 we only have 5 symbols. 0, 1, 2, 3, 4. As an example, this number 12403 in base 5, this is how we note base 5, equals to this number 3 times 5 to the power of 0 plus 0 times 5 to the power of 1 plus 4 times 5 to the power of 2 plus 2 times 5 to the power of 3 plus 1 times 5 to the power of 4, which eventually equals this number. If you calculate this, you are going to get 978, which is the result in base 10. We can say that we need more digits in base 5 to represent the same number which has only 3 digits in base 10. Base 2 is about the lowest that we can get while still having a useful experience. In base 2 we only have 2 symbols, 0 and 1. Every binary digit, or every digit in this base, is called a bit. As an example, we can look at this number, 1101, in base 2. This number equals 1 times 2 to the power of 0, plus 0 times 2 to the power of 1, plus 1 times 2 to the power of 2, plus 1 times 2 to the power of 3, which equals 13 in base 10. It is pretty interesting that this number, 13, which looks pretty short in base 10, is much longer in base 2. It has 4 digits in base 2. You might be wondering, what is it like to live with base 2 based numbers? Or maybe what is it like to live in base 2? Well, life in base 2 is mostly like in base 10. Everything is pretty much the same. Everything that you have learned about base 10 pretty much applies to base 2. And maybe the life in base 2 is slightly even better. Maybe mostly because of the simplicity. We only have 2 digits to deal with, 2 digits to remember. Addition in base 2. We already know how to add numbers and subtract numbers in base 10. So I want to discuss how it works in base 2. It is pretty much the same, but I want to make sure that we are on the same page here. Addition is done just like in the decimal case. We align the 2 summands to the right, and then we add digit by digit. This is how you learned it at school. Addition is done just like in the decimal case. We align the 2 summands to the right, and then we add digit by digit. This is how you learned it at school. If the sum is larger than the base, if the sum of two digits is larger than the base, then we move the carry, or what is left from the addition, to the next position. Some basic examples. 0 plus 1 is, as you probably expected, 1. 1 plus 1 is 10. If you think about it, the next number after 1 in base 2 is 10, because we don't have any more digits. It is like thinking about the decimal case of what is the next number after 9. It is 10, because we don't have any more digits. Another example, 11 plus 1 is 100 in base 2. And maybe another example of this type, 1111 plus 1 equals this number, 1 followed by 4 zeros in base 2. Let's take a look at a larger example to understand how to invoke addition. We want to add those two numbers. We are going to do it just like in base 10. We put the two numbers aligned to the right, vertically, and then we add digit by digit. And we consider the carry, if we get any carry. So let's begin. We first add those two digits. 0 plus 0 equals 0. Next we move on to the next digit. 1 plus 1 equals 10. So we put the 0 here and the 1 here. Next we add 1 plus 1 plus 1 and we get 11. 1 goes here and the other one goes here. Next we add 1 plus 0 plus 1, which equals 10. The 0 goes here and the 1 goes here. Finally we have 1 plus 1, which equals 10. So the 0 goes here and the 1 goes here. Or maybe we could just put the 1 here. And this is the result that we get. Subtraction in base 2. We'll begin with a simple example where we don't have to do any kind of borrowing. 1101 minus 100 in base 2. We begin as usual by writing those two numbers vertically, aligned to the right. And then we subtract digit by digit. We begin with the first two digits. 1 minus 0 equals 1. Next we move on to the next pair. 0 minus 0 equals 0. And then we have 1 minus 1 equals 0. And finally 1 minus nothing, which is basically 0, is 1. And we get this result. This was a pretty simple example. Let's take a look at something more complicated. 100 minus 1. We first write those two numbers vertically and align to the right. Now we want to subtract 0 minus 1. And we can't really do it because 1 is larger than 0. The solution is to borrow from one of the higher digits. So we borrow from this digit, which is the first one digit inside this number. The borrowing changes this digit from 1 into 0, and then we get 10 units in the next location, in the next position. From those 10 units, we also want to borrow 1 unit. We borrow 1 unit to the right, and we are left with 1 in this position, and we get 10 in this position. Now we can subtract 10 minus 1. and we get as a result 1. Next we subtract 1 minus nothing, or 1 minus 0, which is 1. The result that we finally get is 11 in base 2. By now you've probably noticed that in some cases subtraction could be less fun than addition, because we have to borrow from some distant digit sometimes. Another example, and this is about as complex as it gets. We want to subtract this number from this number. As usual, we first write those two numbers vertically aligned to the right. We begin with 0 minus 0, which is 0. Next, we should subtract 0 minus 1, but we cannot do it, so we have to borrow. We borrow from the next digit, which turns this digit into 0, and when we borrow 1 unit, it represents 10 units in the next position. So we just subtract 10 minus 1, and we get 1. Next, we want to subtract this pair, which is 0 minus 1. And we cannot do it because 1 is greater than 0. So we have to borrow. We have to borrow again. We borrow from this digit. This digit is turned into 0, and we get 10 at the next position. Next we take 1 unit from here, which turns this into 1, and we get 10 in the next position. And finally we borrow again, and we get 10 here, and those two digits are now 1. Now we can actually do the subtraction. We subtract 10 minus 1, and we get 1. Next we subtract 1 minus 0, and we get 1. And finally, 1 minus 1 equals 0. And this is the result we get in base 2. Exercises. There are some exercises for this lesson, and they are very important. Some of them are about adding numbers and other about subtracting numbers. And there are some more interesting things. If this is your first time encountering base 2, it is very important that you do all the exercises. Make sure to go one by one and solve all the exercises. It is the basis of all the other parts of the course. You have to understand the binary base to be able to do the rest of the course. So enjoy yourself and see you on the next lecture.